This Mathcast will walk you through section 10.1 of the CPM Calculus text, where your students will develop a variety of ways to test an infinite series to see if it converges or diverges. Section 10.1 is a lengthy section, complete with 8 lessons that explore a variety of tests that can be used to determine if an infinite series converges or diverges. Recall that the concept of convergence and divergence was first explored in section 6.5 on improper integrals, and converging and diverging series were also examined in section 9.1, but through the lens of geometric and telescoping series only. Lesson 10.1.1 starts with problem 10-1 that explores the convergence of the infinite series 1/2 plus 1/4 plus 1/8 and so on. This, of course, is a geometric series whose first term is 1/2 and whose common ratio is also 1/2. So by now your students should easily be able to argue that its sum is 1, either using the a over 1 minus r shortcut or by using a system of equations. Both of those strategies were reviewed in Chapter 9. Or they can go about it in an entirely new way, using this geometric representation drawn here and in their student text, which teams will deconstruct to show that the whole is the sum of these infinitely many parts. So this opening problem aims to show that there are multiple ways to think about the sum of a series, and the rest of this lesson will be dedicated to thinking about whether a variety of infinite series will be finite or infinite. Then, the rest of this section will be dedicated to discovering discrete ways to prove or test whether a series diverges or converges. Problem 10-2 will take the entire period. In this problem, your students will be given a set of 12 series, each in expanded form. Working in teams, the first challenge will be to rewrite each of these series using sigma notation. And the second challenge will be to try to figure out, that is to predict, which of these series will converge and which will diverge. Remember, this is just a prediction. By the end of these 8 lessons in this section, your students will learn a variety of tests that they will use to confirm with accuracy whether their predictions on this day were correct. In fact, each lesson in this section will feature a different convergence test, and the very last question of most lessons will ask students to go back to this set of problems, 10-2, and check to see if the test that they learned that day can be applied to any of those series, and then to refine their work accordingly. So permit your teams to be wrong today. Allowing errors will make the aha moments later on in this section all the more powerful. For example, many students might incorrectly assume that the series in part L will diverge because the nth term of the series approaches 0. Now, there's some good common sense thinking in this, but in just a couple of days, your students will learn to prove that a series like this will converge by the integral test or by the p-series test. So allowing them to be incorrect now will make the future a little bit more memorable. So most of these predictions will be yet to be proven. However, you will see your students use a variety of creative techniques to reach a conclusion. For example, some teams might use technology to graph the first few terms of the sequence of partial sums and try to predict whether the graph has a horizontal asymptote or not, and if it does, they'll say the series converges. Others might attempt to integrate the argument of the series from 1 to infinity as a way to make a prediction, and still others might attempt to use the sum of a geometric series formula, the a over 1 minus r, even though only 2 of these series are geometric. These teams might somehow approximate a common ratio, and if the common ratio that they approximate is between -1 and 1, they'll conclude that the series converges. Now, though none of these techniques are entirely correct, all of them are connected to a convergence test technique that they will be learning in the near future in this section. Remember, problem 10-2 does not end here. Almost every lesson in this section will end with a question that asks your students to refer back to this problem set and to refine their work using new convergence or divergence tests that are discovered. So it's a good idea to have your students do this lesson, 10-2 in particular, on a sheet of paper that they can easily access, like a bright colored paper, and so they can keep that in their notes ready to go from day to day. Lesson 10.1.2 introduces the divergence test, which is also commonly known as the nth term test. Though the divergence test is introduced here, do not expect your students to entirely master it or to really appreciate it for at least a few more days until they've encountered a number of the other tests for convergence or divergence. Now, problem 10-13 presents the divergence test in a very intuitive manner, and students will summarize it by completing the math note, which is right below part E of this problem. But the most interesting and the most confusing part of the divergence test is that its inverse does not always hold true. That is, if the nth term approaches 0, then it is actually indeterminate if the series will converge or diverge. Part A of problem 10-14, however, pushes students to make a false conjecture about the inverse of the divergence test. And then part B challenges them to think of a counter example, but many students will not be able to do this at this point. So part C breaks the news that, well, it says, it may surprise you that there are counterexamples. The divergence test guarantees that a series will diverge. However, the inverse of the divergence test does not guarantee that the series will converge. It also tells them that the rest of the lessons in this section will focus on these cases where the nth term of a series is approaching 0, so the divergence test is inconclusive. And as promised, the last classwork problem in lesson 10.1.2 will direct your students back towards the set of problems from the previous lesson, problem 10-2, and will challenge them to identify from this set any series in which the divergence test can be applied. That is, the nth term does not equal 0, and then take that moment to verify or to disprove their predictions from the day before. Lesson 10.1.3 introduces the alternating series test. Your students will discover this test by playing a game. Problem 10-25 explains how to set up this game as well as the game rules. It explains that there will be 5 rounds to this game and that each round will feature a series that, as part of the game, will be proven to converge or to diverge. Your teams will need to prepare their own materials to play this game. They will need to prepare a number line, numbered only from -3 to 3, but those numbers should be stretched out as far as possible, so cutting a strip from the long side of a sheet of paper would work well. However, an even longer paper would be better. They will also need a game piece, just one, something small and narrow. Unwinding a paper clip or using the small pointy part of a pencil cap eraser works well. Now teams will split into 2 smaller teams and compete against each other in rounds. One small team will be called team convergence and the other team divergence. For each round, the whole group will play together, and if the series that they're testing ultimately converges, then team convergence will win a point in that round. But if the series ultimately diverges and everybody agrees that it does, then team divergence will win. They're going to keep playing until both sides are convinced who the winner will be. The teams split into 2 teams, team convergence versus team divergence. After drawing a number line from -3 to 3, the first team puts a game piece on the first term of the series. In this case, it's -3. Then the other team computes the next term of the sequence and adds or subtracts it from the previous sum to find the second partial sum, which in this case is -3 plus 5/4 equals -1.75. And they move the game piece by adding or subtracting that next term to the series as a whole. There's the new location. And play continues until both teams agree that the series will converge or diverge. And as you can see, this series converges on a sum of a little bit less than -2. After playing 5 rounds, the text prompts students to record a conjecture about the conditions in which an alternating series will converge. They can use their own words, but this happens in such a structured way that makes it easy for the teacher to quickly check for mathematical accuracy as they circulate. And the lesson concludes with a set of problems in which the students apply their conjecture. More practice opportunities will be threaded throughout homework, starting this night and spaced throughout the course. And we conclude this lesson by returning to the set of series from problem 10-2 and identifying which ones can be proven to converge or diverge by the alternating series test. Students will pull out their work from lesson 10.1.1 and refine their predictions on the series that apply. Lesson 10.1.4 presents the integral test. So naturally, the first problem, 10-36, reviews how to evaluate improper integrals where the upper bound goes to infinity. This will give you an opportunity to supervise your students as they practice rewriting improper integrals as limits and then evaluating those limits. This was a skill they developed back in section 6.5. Now, your students will be reminded that improper integrals sometimes converge and sometimes diverge. So, as you circulate, ask each team to discuss and make predictions about how this concept of converging and diverging integrals might be connected to determining the convergence and divergence of infinite series. And after a bit of time at their table, pull the whole class together for a whip around, which is a study team strategy where a topic is posed and then everyone has an opportunity to share an observation, prediction, or comment briefly with the whole class. Some students might share that both 1 over x and 1 over x squared have y values that approach 0. However, their integral values do not behave consistently. Problems 10-37 and 10-38 both use resource page 10.1.4, so distribute one resource page to each student in your class. In these problems, we will examine the infinite series for 1 over n and 1 over n squared, which will be called Series A and Series B. First, your students will compare the graphs of these series with the graphs of their corresponding functions, 1 over x and 1 over x squared, noting that both series and both functions decrease, and that each function goes through all the terms of its corresponding series. Also, it is no coincidence that these two functions were the integrands of the two improper integrals in the previous problem, 10-36, and that the integral of 1 over x was found to diverge while the integral of 1 over x squared converges. Next, your students will compare the sum of each series with the area under each function. The sum of the series can be represented as the sum of left endpoint rectangles, where each rectangle has a width of 1. Your students will note that in both cases, the left endpoint sum has a greater area than the actual area under the curve, well, because the curve is decreasing. For Series A on the left, this is a visual demonstration of a proof that the infinite series of 1 over n diverges just as the integral does. That is, since the area under the rectangles are equivalent to the sum of the series and greater than the area under the curve of 1 over x, which diverges, then naturally the series must diverge as well. Unfortunately, we cannot use the same argument for Series B. Series B does not work so nicely because it is larger than the area under 1 over x squared, which converges. However, Part D of this problem, 10-38, will suggest a way to slightly adjust the sketch to demonstrate visually that Series B will converge as expected. The way Part D of problem 10-38 does this is to guide students to imagine removing the first rectangle from the Riemann sum for Series B, which notably has a finite area of 1 square unit, and then shifting the remaining rectangles 1 unit to the left. This new set of rectangles represents series B minus the first term, which was equal to 1 square unit. And since this shifted set of rectangles now lies below the function, their overall area, whatever it might be, must be less than the area under 1 over x squared, which we know converges. So series B minus 1 must converge as well. And as for series B itself, well, adding 1 to a converging value will result in another converging value. And this is how we can visually represent that the series for 1 over n squared converges just like its corresponding integral. After completing these demonstrations, your students will complete a math note demonstrating that they understand how the integral test works. Namely, a series will behave in the same way as its corresponding improper integral to infinity. If the integral converges, then so does the series. If the integral diverges, then so does the series. And problem 10-40 gives teams some class time to practice applying this test. Problem 10-41 is a neat problem, but if you do not get to it before the bell rings, that's okay because this topic will come back later in this chapter in section 10.4. So, having just explored the idea that the infinite series for 1 over n diverges, and also having just studied the alternating series test in the previous lesson 10.1.3, this is a natural moment to name this series as the harmonic series and to introduce the notion of conditional convergence, because the alternating version of the harmonic series converges while the non-alternating version diverges. Again, the topic of conditional convergence is introduced here, but will come up much more explicitly later in this chapter. And this lesson ends like the others. Students will return to the set of series from lesson 10.1.1, problem 10-2, and identify those series that the integral test can be used to determine convergence or divergence, and also to confirm or to refute the predictions that they made during the first day of the chapter. Lesson 10.1.5 is a quick lesson that summarizes the p-series test, which states for an infinite series of the form 1 over n to the p, where p is a constant, if p is greater than 1, then the series will converge. Otherwise, it diverges. Students will verify this p-series shortcut by applying the integral test to a set of p-series in problem 10-52, and then they will generalize a rule based on observed patterns. Now recall that this same pattern was found in the second part of lesson 6.5, only in that case it regarded improper integrals, whose integrands had the same form as the argument within a p-series. So expect many teams will be quick to generalize the p-series test. Some students might have held on to the resource page from lesson 6.5. It looks like this. This is a great page to pull out and make connections. On this page, of the 3 graphs, 1 over x is the center graph. So in this case, p equals 1, and the yellow shaded region from 1 to infinity represents diverging area under the curve. Meanwhile, the graph on the left has a p-value greater than 1. Notice that in this case, the area under its curve from 1 to infinity is green, representing that it converges to a finite value. But the graph on the right has a p-series value that is less than 1, and its area under the curve from 1 to infinity is relatively large, and yellow because it diverges. And just like the previous lessons, this one ends by returning to the set of problems from problem 10-2 in the first lesson of this chapter. This time, students will identify series that can be proven to converge or diverge using the p-series test, and they'll use that test to confirm or revise their original predictions. Lesson 10.1.6 introduces the comparison test, that is, the direct comparison test, as opposed to the limit comparison test, which will be the theme of the next lesson, 10.1.7. So keep in mind that this lesson and the next one are closely linked. We'll start this exploration with problem 10-63, which reviews 2 infinite series that students have seen many times at this point. The series for 1 over n, which will be called series Q today, and the series for 1 over n squared, which today we will call series S. Both of these series can be shown to diverge or to converge using either the integral test or the p-series test. Now in problem 10-64, attention turns to just series S and to a new series, series T, which looks a lot like series S. In fact, it looks so much like series S that it's tempting to claim that it must converge as well. Now, as an aside, the integral test could have been used to prove the convergence of series T, but the comparison test will be a whole lot easier. So part A has students list the first 4 terms of each series, and then part B has them graph those terms on the same set of axes to reveal that every term of series T is less than every term of series S. So, since we know that series S converges to a finite value, then series T must converge to an even smaller finite value. That is, series T must converge. Now the same process is repeated for series Q in problem 10-65. This time, divergent series Q is juxtaposed with series R, which looks a lot like it. In this case, the terms in Q are a bit smaller than the terms in R. So since Q diverges, R, which has, dare I say, a larger sum, must diverge as well. And based on these examples, students then summarize the comparison test in a math note in problem 10-66. In this statement, the terms in S are said to be less than the terms in T. So if T converges, then S, which is smaller, must converge as well. Likewise, if S diverges, then T, which is larger, must diverge as well. Problem 10-67 allows students to play a bit with the comparison test. In part A, they're given a series T that they know converges by the p-series test. Their challenge is to write a similar looking series whose terms are all a bit smaller, so must converge as well. Likewise, in part B, they're given a series W that they know by the p-series test must diverge. And students must write a similar looking series that must diverge as well because the terms are all just a little bit bigger than the terms of W. Through doing a problem like this one, you will find that while strengthening their calculus skills, some students will be simultaneously strengthening their fraction sense as well. And then once this is complete, problem 10-68 provides a mixed set of practice problems allowing teams to practice choosing a strategy to justify the convergence or divergence of a set of series. The next lesson, 10.1.7, introduces the limit comparison test, which is a strategy that is commonly used when the direct comparison test is attempted but fails, because the terms of the unknown series are neither smaller than a known converging series nor larger than a known diverging series. Now, this lesson features a humorous dialogue between 2 calculus students named Harry and Henrietta, who, through their emotive exchange, help each other to discover the limit comparison test. And this dialogue continues throughout the first 3 problems in this lesson. So a great study team strategy to use to make these problems and this dialogue very powerful is the fishbowl. Use this strategy 3 times. Once after teams complete problem 10-76, and again after they complete 10-77, and finally after they complete 10-78. Now, the way this would work is you'll choose 2 students from the class to play the role of Harry and Henrietta. And then, after all teams have completed problem 10-76, you'll have the entire class get up from their tables and surround Harry and Henrietta's table, like they're looking in at them like they're fish in a fishbowl. Harry and Henrietta will then recreate for their audience the conversation that was written into the problem that they just completed. Well, some of the dialogue is written in, and some they will have to improvise. Then, when they're done recreating this conversation, you can have a short conversation with the entire class that's huddled around to summarize what they noticed or what they predict. and then send all teams back to their tables to do problem 10-77. And once again, when everyone is done, have them gather around and do another fishbowl, recreating the conversation between Harry and Henrietta in that problem, followed by a short whole class debrief, and then repeat once more for problem 10-78. Briefly, problem 10-76 introduces the need for the limit comparison test by demonstrating a couple of situations in which the direct comparison test does not work, even though two series, like these, appear to be very similar to each other. Harry is convinced that since series S diverges by the p-series test and the denominator of series T has the same power as S, then they both should diverge by the comparison test. But Henrietta slows him down, arguing that the terms of T are smaller than the terms of S, not larger. And then they run into similar trouble when comparing the convergence of series W to series U, whose denominator is also to the second power, but the terms are larger. And Harry is heartbroken because Henrietta has convinced him that the comparison test will not prove what seems to him to be so obvious. Now, once all teams have reached this stopping point, this is where you pull the class together to do a fishbowl. Act out the dialogue between Harry and Henrietta, some of which is scripted into the problem and the rest will need to be improvised, and then summarize as a whole class. Now in problem 10-77, Harry has not completely lost hope that series S and series T will both diverge. So in part A, he considers a few select terms of each series, like the 10th term and the 100th term, and then he compared them using ratios. And based on the pattern he saw with these ratios, he used a limit to determine the ratio between the nth term of S and the nth term of T as n approached infinity, and he found out that that limit was finite. Now this problem leaves off here, so this will be an opportune moment to do another fishbowl. This builds the suspense and allows the class to pause and make predictions about the significance of that finite ratio before they move on to the next problem. Problem 10-78 will investigate a situation in which the limit comparison test, which was just discovered, yields a finite value of 0. In this case, the infinite series for 1 over e to the n minus 1 is being compared to the infinite series for 1 over n squared. And thinking that they should behave the same way, Harry sets up a limit between the terms and gets the value of 0. And from that, he concludes that they will both converge because 0 is a finite value, so the ratio must exist. But when Henrietta completed the limit comparison test, she got an infinite result. And so she wonders if that might mean that the series actually diverges. So this time, Henrietta is awfully frustrated, and she decides to do another limit comparison test to a diverging series, 1 over n, but she still does not achieve a finite limit. Alas, Harry saves the day by comparing the infinite series to 1 over e to the n, which looks a lot more like the series in question, and he knows it converges. Happily, that limit yields a non-zero finite result. After completing this problem, do one more round of fishbowl. And then have students complete the math note that says, if the limit to infinity of the ratio of the terms between two series is finite and not 0, then both series will converge or both series will diverge. And consistent with the previous lessons, we end lesson 10.1.7 by returning to the set of problems from the first day of this chapter. This time, students will identify the series that can be proven to converge or diverge using the limit comparison test. And they'll use this test to confirm or to revise their original predictions. The final lesson in this section will introduce the ratio test, and the ratio test is presented as a way to pretend that a non-geometric series is a geometric series, and then use the convergence rules for a geometric series to determine if the non-geometric series converges or not. Now, the first problem in this lesson, problem 10-90, reviews what those rules are. That is, geometric series will converge when the absolute value of r is less than 1. Now be sure to go over this problem with the whole class at the beginning of the lesson, as this fact will be referred back to again and again throughout this lesson. Now, problem 10-91 has students explore a series T, which is an infinite series for k over 2 to the k. Not only is T not geometric, but none of the 6 tests that students know at this point will be able to prove whether T converges or diverges. So part C asks students to pretend that the series T was geometric, and then playing that pretend game, find out what the value of R would be by determining the ratio between successive terms of T as those terms approach infinity. Now this limit turns out to be 1/2. So our pretend geometric ratio is 1/2, which means that if T were geometric, it would converge by the rules of the geometric series tests. In problem 10-92, your students will complete their final math notes box summarizing the ratio test, which ends up looking almost identical to the test we use for geometric convergence. Of course, one thing is left out. What if r equaled 1? To explore this issue, part B has them apply the ratio test to 2 very familiar series. The first one, the harmonic series, we know diverges, and the second, 1 over n squared, converges. And that fact could be proven using the p-series test or the integral test. But when we use the ratio test on these series, both result in an r value of 1. So sometimes r equals 1 means divergence, and sometimes it means convergence. With that, your students will add the stipulation to their math notes that if r equals 1, then the ratio test is inconclusive. And lesson 10.1.8 ends like the others. Students will return to the set of series from lesson 10.1.1, problem 10-2, and identify the series that the ratio test can be used to prove convergence or divergence. In the process, they will confirm or refute the predictions that they made during the first day of this chapter. One last note about section 10.1, which covered 7 different convergence or divergence tests for infinite series. Throughout this section, your students completed their own math notes in a scaffolded, fill-in-the-blank sort of manner. But be aware that formal math notes for all convergence tests can be found at the very end of Chapter 10, after Section 10.4 is complete. So this concludes the walkthrough of Section 10.1, where students learned a variety of ways to test an infinite series to see if it converges or diverges.